Chapter 12 covers electromagnetic waves. We call it the electromagnetic spectrum. Now, you've already been discussing Chapter 10, which is transverse and compressional or longitudinal waves. But we're going to discuss electromagnetic waves, which are slightly different. So as a brief review, let's go through what the difference between a mechanical wave and an electromagnetic wave is. A mechanical wave, which is a transverse wave or a compressional wave, waves that require a medium in which to travel. So they're quite different from an electromagnetic wave because an electromagnetic wave does not require any kind of medium. And we want to also define what an electric field is. That's a region in which particles can be pushed or pulled. Now, this is going to be important when we talk about electromagnetic waves. So let's talk about the nature of electromagnetic waves. They are transverse waves. However, they don't require a medium at all. That's why they can travel through space. And as they travel, there are electrical and magnetic fields. And those electrical and magnetic fields travel together. And I'll show you a brief example here in a moment. And they can travel really, really fast at about 300 million meters per second, which means the sunlight that you are seeing today is about 8 minutes old. And that's how long it took to travel the 150 million miles from the sun to the earth. So you're actually, when you go outside today at lunch, will be seeing 8-minute-old sun. So let's look at these electromagnetic waves. Okay, they have an electric field and they have a magnetic field. And the interesting thing to this is when you actually have an electric field and it is vibrating, it creates a magnetic field. And when you have a magnetic field that is traveling and vibrating, it creates an electric field. And the result is the electromagnetic wave. And this is what it looks like. So you see how you have the red transverse wave, and you've got the blue transverse wave, and they are traveling together. One of them is an electric field, the other one's a magnetic field, and they are causing each other to constantly be in action. Okay, so as I already said, when we actually have an electromagnetic wave, we can think of them as a stream of particles, as the animation at the bottom shows. And that stream of particles, you know, is light. And we can tell about light waves by putting them through different lenses. We can tell by putting them through a prism. And anytime that you have some light and it's directed at something, it's called a photoelectric effect. So it can actually knock electrons off of substances, and that's our photoelectric effect. So here are some of our, or all of our, I should say, electromagnetic waves. And in the electromagnetic spectrum, we put them in order, and if you look here at the very bottom, you will see a longer wavelength and a shorter wavelength. So we put them in order of increasing frequency. So we've got our radio waves, and then the next most frequent is a microwave, which actually a microwave is a radio wave. Then you have infrared, visible light, which is the visible light spectrum you've probably heard several times in the past. It's called Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Those are the lights that we can see. Then you have ultraviolet, X-ray, and gamma. So let's talk about radio waves. Radio waves have the longest wavelength and the lowest frequency. Remember that inverse relationship. And when you have a radio, you actually pick up those radio waves, and in your radio is something called a transistor that changes those radio waves into sound waves so that you can hear them. And we talked about, when we were originally talking about radio waves, that each radio station broadcasts on a different frequency. And those different frequency If they're FM, that's frequency modulation. And if they're AM, it's amplitude modulation. So it just depends on how they pick up the waves and then how the transistor changes them. Another way that we use radio waves is with an MRI. An MRI stands for magnetic resonance imaging. And what happens if you've never had an MRI, it's kind of a tube-like apparatus that they put you into, and then there are huge magnets that go around you. And when you're in it, it makes this thump, 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 thump sound. And what it's doing is using those magnets to be able to take pictures, and they can actually take little tiny slices and look at your brain or look at your heart or look at the arm or whatever it is that they need to discover. And they use those radio waves and they use a magnet to be able to do that. Hence the name magnetic resonance imaging. And here's just a picture of an MRI of the brain. Just shows you, and they can actually just take little slices of that. Now, I already talked about amplitude modulation, and you all remember what amplitude is. Basically, amplitude is how high the crest of a transverse wave goes above rest or equilibrium. And AM stations, they bounce off. Okay, they're actually sent out and they bounce off the sky. And that's why at night, when it's really, really clear, sometimes in this area we can get radio stations from California, Colorado, Texas, because there's not a lot of interference. So they actually, AM bounces them off of the sky. So that's why AM stations are a little harder to pick up if you're going through the mountains, because they sometimes have interference. Now, the same thing can happen with FM or frequency modulation. They go in a very straight line. So you can lose reception when you travel out of range. And so anyway, the thing that I have found, at least, is with the FM stations, they usually come in a little bit louder and clearer. But then when you get out of range, they're just gone. Where with the AM stations, you may still be able to slightly pick them up because it doesn't travel in a straight line, but they start getting fuzzy. So this shows you where radio stations and TVs and microwaves are actually, where they actually are used. And so this is the spectrum that they're in, and it shows you the wavelength and the frequency. And it is this frequency that you actually tune to.